And a mysterious visitor is on its way to Earth, moving closer, 137,000 miles per hour. Is it an alien ship, a comet? Scientists and researchers are left puzzled.
On the 1st of July, NASA detected a mysterious object.
A nuclear-powered spacecraft sent by aliens.
3I Atlas was an interstellar visitor.
Something is racing through the void, a fragment from the uncharted reaches between the stars, breaching the border of our familiar solar system at astonishing speed. Just days ago, astronomers around the world began grappling with an electrifying question. What has arrived, and what might it reveal about both our solar system and the broader cosmos? On July 1st, 2025, as faint pre-dawn light crept across the Atacama Desert in Chile, the Atlas Survey Telescope, funded by NASA and designed to search for approaching asteroids, captured a fleeting, subtle streak against the night sky. That faint signature, nearly lost in the cosmic haze of routine observations, turned out to be something extraordinary, not consistent with the orbital paths known for solar system objects. Data analysis told an incredible story. Something was inbound, traveling at nearly 61 kilometers per second, and clearly not originating from within our solar system. Astronomers soon realized this was a true interstellar visitor, now officially labeled Comet 3, I/ATLAS, the third such object ever identified. The announcement reverberated throughout the scientific community. Only twice before had an object from interstellar space been observed passing through our solar system. The mysterious Oumuamua in 2017, and then Comet Borisov in 2019. These rare finds are far from mere curiosities. Each has the potential to shed new light on the nature of the cosmos. Shaped by processes and chemical environments outside our experience, interstellar objects act as natural probes from regions of space we might never explore directly. Some researchers suggest they could help explain how vital ingredients, like water, first arrived on Earth. Others note that unfamiliar bodies might pose previously unrecognized risks as well as opportunities. With telescopes around the world now focused on this new arrival, and scientists revising models as new data comes in, the universe has presented us with another remarkable opportunity to study an emissary from the depths between stars. The mysteries are many. Will 3I/ATLAS hold clues to the origins of water and organic compounds in the solar system? Will it survive its brush with our sun? And perhaps most compellingly, what, if anything, does it carry with it from its long journey through interstellar space? What can we actually learn from this object accelerating into the heart of our solar system? A third message: the history of interstellar intruders. For centuries, astronomers believed the dramas of our solar system played out in isolation. Planets, asteroids, and comets were assumed to be the sole offspring of our sun, locked within its family and moving in familiar elliptical orbits. The idea that objects might cross the vast gulfs between stars and enter our cosmic neighborhood was the subject of speculation, but never observation. That changed in October 2017, when astronomers detected an object unlike any before, Oumuamua. It followed a hyperbolic trajectory, passing rapidly through the solar system before escaping, never to return. Oumuamua's elongated shape puzzled observers, and its motion, accelerating slightly as it receded from the sun, with no clear evidence of outgassing, prompted scientific debates that continue today. Was it a fragment of a larger planetary body, an unusually shaped comet, or even a product of alien engineering? Observational opportunities were fleeting, and many questions remain unanswered. In 2019, astronomers identified 2I/Borisov, a more familiar-looking comet that nevertheless originated from interstellar space. Unlike Oumuamua, Borisov displayed a classic cometary tail with water vapor and dust streaming off as it approached the Sun. Spectroscopic data revealed that while broadly similar in composition to solar system comets, Borisov also showed distinct differences, reminders of its exotic origin. Now, with the discovery of 3I/ATLAS, we have another chance to expand our sample of interstellar guests. In cosmic context, 3 is only a beginning, but it transforms what was once an anomaly into a pattern. Far from being isolated, our solar system seems to be open to visitors from the greater galaxy, objects traveling for millions or billions of years, offering us glimpses into the processes shaping planets, debris disks, and perhaps even the seeds of life elsewhere. A natural question arises. Why are we now spotting interstellar objects, seemingly in a quick succession after millennia of silence? The main answer is technological. Modern survey telescopes like ATLAS are more automated, sensitive, and comprehensive than any before. Increased vigilance means even fleeting visitors, detectable for just days or weeks, may now be registered and tracked. Our solar system, always permeable, is finally being observed with a sharp enough eye to notice these interstellar crossings. What we will learn from more frequent encounters remains to be seen. Each new arrival challenges our theories and expands our view of the possible, tracing the trajectory, the anatomy of a discovery. In the earliest hours of July 1st, 2025, the ATLAS telescope in Chile executed its nightly search for near-Earth objects. It gathered images of the night sky, comparing them against known star fields, hoping to spot asteroids that could pose impact threats. Amidst that routine, analysts detected a moving object whose speed and trajectory stood out. Upon computing its orbit, it became clear that this object's path was highly hyperbolic, an open curve, indicating it was not gravitationally bound to the Sun. Unlike typical comets and asteroids, this visitor was plunging toward the Sun on a one-way journey, destined to exit the solar system forever after its brief encounter. Within days, the international astronomical community coordinated to observe, confirm, and publicize the findings. The Minor Planet Center, responsible for tracking such phenomena, provided an official designation: 3I/ATLAS. 3I stands for Third Interstellar Object, while Atlas credits the system that first detected it. The object's pre-discovery inactivity, meaning it was undetected before Atlas's observation, shows the challenges inherent in finding such fast, faint travelers. Even now, as 3I/ATLAS approaches, it remains faint and hard to study in detail. Its brightness varies subtly, perhaps due to rotation or the formation of a cometary coma as sunlight heats its surface. Preliminary photometry suggests it differs in color from most native asteroids and comets, hinting at a composition shaped by conditions beyond our solar system. Astronomers worldwide are mobilizing to collect every possible photon. Optical telescopes seek to refine the orbit and capture changes in brightness. Infrared and spectroscopy instruments will attempt to characterize its chemical makeup. Radar is unlikely to give much. Most cometary nuclei are too small and fragile for significant radar returns at such distances, but every possible avenue is being explored. The observation window will be brief. As the comet swings around the Sun, it may become brighter and behave in unpredictable ways. Every data point counts. Each image, measurement, and spectrum has the potential to increase our understanding not only of 3I/ATLAS, but also the wider processes that sweep material between stars. What insights might be encoded in the dust and ice of this ancient traveler? A threat and a promise. What interstellar objects carry? With each new interstellar object, astronomers weigh both promise and risk. These visitors could be cosmic couriers, bringing chemical and physical information about distant planetary systems. Ancient comets like these may have delivered water, organics, and even prebiotic molecules to young planets. If so, the basic conditions for life may be more widely distributed than once believed. The 2019 passage of Borisov, for example, gave scientists a rare chance to test these ideas. As it raced through the inner solar system, Borisov's coma was found to contain familiar compounds: water vapor, cyanide, carbon dioxide. The ratios, however, were distinct from those in familiar comets, hinting at different formation environments. Intriguingly, Borisov confirmed that at least some of the fundamental building blocks are widely spread across the galaxy. But these objects are not guaranteed bearers of life. Their contents are often uncertain, especially before they approach the Sun, and their chemical mix may include compounds rare or absent from local space. In terms of risk, any object traveling tens of kilometers per second through the solar system exercises enormous kinetic energy, yet current models do not predict a collision between 3I/ATLAS and Earth or any other planetary body. Instead, the primary scientific concern is understanding its internal structure, chemistry, and possible activity as it nears the Sun. Speculation about dangers such as unknown viruses or unique pathogenic agents locked in primordial ice is, at present, unsupported. There is no current evidence that such risks exist. Nonetheless, the unpredictability of these objects' behavior, the possibility of fragmentation, explosive outgassing, or volatile interactions with solar heat, remains an area of active study. Comparing 3I/ATLAS's observations to those of Oumuamua and Borisov will be crucial. All three are interstellar, but manifested very differently. One apparently inert, one a classic comet, and one 3I/Atlas, whose true nature remains to be revealed. Will this new arrival reinforce what we think we know, or upend our understanding once again? Every encounter is a new data point for both scientific optimism and prudent vigilance. The Sun's judgment. Will 3I/ATLAS survive the encounter? Interstellar space is profoundly cold and quiet, a repository for the relics of star formation and planetary building. But as 3I/ATLAS closes in on the Sun, it will endure a powerful transformation. Solar heat is both a revealer and a destroyer. It can vaporize ancient ice and drive spectacular displays, or disintegrate fragile nuclei so thoroughly that little remains to study. Astronomers remember how Comet Borisov, for all its brilliance, succumbed to the Sun as it neared perihelion. Tidal forces and intense heating broke the nucleus into fragments, rapidly dispersing its tail. Conversely, Oumuamua, perhaps rocky rather than icy or protected by a hardened crust, passed through the Sun's influence largely unchanged, showing no obvious activity. So what outcome awaits 3I/ATLAS? Predictions are difficult. If it is primarily icy and fragile, as are many long-period comets, the Sun's heat could cause it to shed its outer layers, brighten dramatically, and perhaps break apart. Alternatively, if it is rocky or has a thick, devolatirized crust, it could survive perihelion and exit the solar system largely intact, carrying its secrets with it. Observatories around the globe have reprioritized to maximize data collection during its closest approach, when cometary activity, the formation of a coma or tail, is most likely. Models and predictions are constantly being updated as new observations trickle in. The survival or disintegration of 3 I/ATLAS will depend on the specific mix of materials, porosity, and structural integrity that has been shaped by millions or billions of years in deep space. No matter the outcome, it will add another vital chapter to our record of interstellar objects. This is more than a question of curiosity. Each observed behavior teaches us not just about this one comet, but about the diversity and fate of objects ejected from other star systems. How do they persist across the cold expanse? And if they enter planetary systems, how do they interact with their new environments? The answers will help shape our theories about planetary system evolution and the potential for chemical exchange across cosmic distances. Decoding the signal, what we can learn from the data. 3I/ATLAS acts as a natural probe, offering a rare chance to study the chemistry and physics of another star system, perhaps even from a time before our solar system formed. Its dust, ices, and surface features may encode a record of processes now long extinct. As it nears the Sun and perhaps sheds material, astronomers will attempt to analyze the composition of the coma and tail, if one forms, using spectroscopy. The ratios of different isotopes, such as hydrogen, oxygen, or carbon, in emitted gases may reveal the kinds of stars and protoplanetary disks that gave rise to the comet. Organic compounds, if present, will be sought with particular interest, as they bear on questions of chemical universality and prebiotic chemistry. Unlike missions able to sample or return material, ground-based and space telescopes must work with light alone, deconstructing the spectral fingerprints of molecules and minerals across the electromagnetic spectrum. Instruments will search for signatures of water, carbon monoxide, cyanide, and simple organics. Compounds also observed in other comets and interstellar molecular clouds. Comparisons between the chemistries of Oumuamua, as inferred from its non-activity and reflectance, Borisov, and 3I/Atlas will be central. Even among so few objects, patterns or striking anomalies may begin to emerge. Unraveling these signals is challenging. Background light from the Sun, instrumental limitations, and the comet's faintness hinder data collection. Nonetheless, each successful observation provides a test of our ideas about planetary formation, galactic chemical evolution, and the potential for processes like panspermia. Do the materials found in 3I/ATLAS match what we see in our own solar system's comets, or do they hint at wider diversity? What does this tell us about the environments from which such objects are ejected? And could such reports one day inform us about the formation or destruction of other planetary systems? As scientists analyze the data, we edge closer to understanding the big picture, how matter cycles through stars and planets, and how the boundaries of solar systems are crossed by both random debris and perhaps the seeds of future worlds. A pattern emerges: interstellar visitors and the question of rarity. The sudden succession of 3 documented interstellar objects raises compelling statistical and philosophical questions. Are we simply in a lucky or unlucky era of sightings? Has our observational technology finally become powerful and vigilant enough to notice frequent events once overlooked? or are external forces, such as the passage of stellar clusters or massive gravitational perturbations, sending more debris our way. Surveys like ATLAS, with broad sky coverage and rapid response, are increasingly capable of detecting objects that would previously have evaded notice. The likely truth is that interstellar travelers have always entered the solar system at an unknown rate, but only now do we possess the sensitivity and computational tools necessary to spot them. The frequency with which we observe such objects could therefore increase as technology improves. However, some researchers do consider the dynamical processes that shape their influx. Close stellar encounters, galactic tides, or the migration of star clusters through the Milky Way may occasionally send a proportionally larger share of debris toward our own system. The diversity among Oumuamua, Borisov, and Atlas, different in both appearance and composition, speaks to the variety of environments and processes across our galaxy. If further observations and improved surveys confirm that interstellar objects are relatively common visitors, it would upend ideas of planetary isolation and reinforce the notion that matter and chemistry are shared and mixed throughout the Milky Way. Alternatively, if the rate remains low, even with the best technology, these objects truly may be rare gems, cosmic flotsam from chance ejections and extraordinary events. Either way, we are now witnesses to a turning point in planetary science. The more we see, the deeper our understanding of planetary system birth, evolution, and exchange across space. How many such visitors have slipped past in earlier epochs, unrecorded and unknown? Technology, more than fate, is opening a new archive of galactic history. The implications, new frontiers in the search for life and the fate of planets. Each interstellar visitor broadens the scientific horizon. They have the potential to answer long-standing questions about the origins of water, organic molecules, and perhaps even the precursors of life on Earth and other planets. If 3I over A TLAS proves to be rich in accessible water or complex organics, and if spectral signatures align with those on Earth, then the theory that critical ingredients for life arrive via cometary delivery receives further support. Such findings would lend credence to the hypothesis that panspermia, the transfer of material capable of seeding life from system to system, is not only possible, but perhaps even common in the galaxy. On the other hand, if interstellar objects turn out to be compositionally different from solar system comets, they may reveal the limits of chemical universality and pose new questions for theories of planetary system formation. These scientific stakes are interwoven with practical considerations. The discovery that interstellar comets and asteroids can transit the solar system poses challenges for planetary defense. Their high velocities and trajectories, shaped by unknown and often chaotic gravitational influences, make predictions and monitoring more difficult. While current assessments do not show impact threats from known interstellar objects, preparedness for such possibilities will require new detection and tracking strategies. Just as important are the cultural and philosophical implications. The routine passage of material between stellar systems suggests that the Milky Way is not a set of isolated islands, but an interconnected archipelago where chemical building blocks and histories circulate. The arrival of 3I/ATLAS stands as both a warning not to ignore potential risks from the unknown and an invitation to curiosity. It suggests a universe richer and more connected than we once believed, and challenges us to look beyond our own narrow context in the search for understanding. As new discoveries accumulate, we will continue refining our ideas about life, planets, and the intricate dance of matter between stars. A moment at the threshold. For now, all eyes and all instruments are focused on the newcomer hurtling through the solar system. 3I/ATLAS is more than a fleeting point of light. It is a tangible link to processes and places unreachable by spacecraft or signal, and a symbol of the dynamic universe that shapes us. As the object approaches the sun, its fate uncertain, so too is the outcome of our investigation. We stand on the edge of discovery and mystery, where each measurement and observation holds the potential to reshape what we know about our origins and our place in the cosmos. In coming months, 3I/ATLAS may brighten into a visible comet, fade quietly into the solar glare, or shatter as it rounds the sun. However brief its visit, it marks a new chapter in our engagement with the wider galaxy, a reminder that barriers between solar systems are not insurmountable and that knowledge is constantly renewed with each messenger from the dark. This is a moment to record and remember, an intersection of chance, science, and cosmic history. As technology sharpens and our curiosity expands, the silent lanes of the cosmos will yield more of their secrets. One stone, one ice crystal, one interstellar emissary at a time. With 3I/ATLAS, we are given one more opportunity to witness, to wonder, and to learn. Our watchfulness, our scientific discipline, and our imagination together ensure that the unknown becomes, step by step, part of our shared knowledge. We are not just bystanders on a quiet planet, but fellow travelers on a journey that stretches from the familiar light of our sun to the deep, ancient, dark beyond.